So we've been talking about region-based analysis, and in this module, I'm going to discuss some examples of region transfer functions. And one example is the symbolic analysis of loops. And we've seen this before, but let's say we have an available expressions analysis, and this is my program that initializes x to 10 and I to 0. And then it has a loop which says if I is greater than or equal to n, go to end, otherwise do x plus equals 2 and I equals I plus 1, and then go back to the loop edge. Now, if I just run an available expressions analysis with my standard gen and kill transfer functions, then I just get bottom for both x and I. But if I use a loop region around it, and then I use a symbolic analysis, and recall what the symbolic analysis involves is basically what is the first value of x and I that's flowing in, which will be 10 and 0 based on available expression analysis, because the value that flows in is a constant, we know that. And then the question is, what is one iteration of this loop doing? And that is, we can figure out that it is a constant addition, plus 2 or plus 1 of a couple of variables. And then we can say what is the number of iterations of this loop that it can execute, which is the loop trip count, which in this example is n. And using that, I can get a more precise transfer function for this entire loop, which is x is 10 plus 2 into n and I is n. And this is an example of a summary transfer function for a loop region for the available expressions analysis to give you more precise answers. I'm going to give you another example of a summary transfer function, but before that I want to define this term called single entry, single exit regions. What is a single entry or SESE region? What is an SESE region? It's a subgraph of the control flow graph with a single entry x, a single exit, let's call it y, and then one constraint which says every CFG cycle that contains x also contains y and vice versa. This is an important constraint, just keep it in mind. We're going to look at examples. So here's an example of an SESE region. So x at the very top, y at the very bottom. This is a subgraph of the control flow graph, and there are all kind of if-then-else edges. There are all kinds of loops. There are cycles which are not necessarily natural loops, but x and y, any cycle that x belongs to, y belongs to as well, and vice versa. In fact, x does not belong to any cycle, neither does y belong to any cycle, and so this is an SESE region. The idea here is that the number of times x executes in any invocation of the whole program, of the whole CFG, is equal to the number of times y executes in the whole CFG and vice versa. And that's why we call it an SESE region. Here's another example of an SESE region. Both x and y are a part of an inner loop. And so, any cycle that x is part of, y is a part of, and vice versa. Here are some non-examples. So here's an example where x is a part of this cycle, but y is not a part of this cycle. Even though there is a single entry, single exit, the third constraint is not being met. So this is not an SESE region. Notice that in this example, x dominates y and y post dominates x, and yet this is not an SESE region. So SESE region's definition is not based on domination and post domination. It is based on the cycles being the set of cycles in which x belongs is the same as the set of cycles to which y belongs. And notice that I'm saying cycles and not necessarily natural loops. Similarly here, this is another non-example. This is not an SESE region because x belongs to this cycle, but y does not belong to that cycle. So when we have meet over paths, when we do a region-based analysis, then we can create a region. And if the region is an SESE region, and it depends on how you create the region hierarchy, but if you decide to create a region for an SESE control flow graph or an SESE region, then you can use a meet over paths summary transfer function. Now here's an example, and we have seen this example before. So let's say this, x and y are getting assigned to 10 and 3, y and on one path and 4 and 9 on the other path, and eventually I'm doing z equals x plus y. Now I can see that irrespective of what path I take, z will always evaluate to 13. But if I use my MFP analysis onto the constant propagation transfer functions, then I'm going to basically get bottom for z because I'm going to meet x and y here, and both x and y are going to turn out to be bottom. And then I'm going to say, what is z equals x plus 5 and x and y are both bottom, that is also bottom. And so that's the answer I'm going to get if I just use my maximum fixed point algorithm, the one that we have, the data flow analysis. But what if we use a meet over paths analysis? So a meet over path would say, let's look at all the paths in this region and compute the transfer functions of all the paths independently. So there are two paths, and in each of the paths, z will get value 13. And I'm going to meet at the very end, and that's why it's called meet over paths. And when I meet over all the paths, then z is actually 13 on all the paths. And this gives me a more precise answer because it gives me 13 instead of bottom for Z. Now recall that when I do mean over parts analysis, the problem is that the number of parts in a program can grow exponentially, and that's why we didn't do it. But when we break down the program into regions, then we can choose to do the mean over parts analysis over smaller regions. For example, if I'm able, maybe the transfer function of the region, the summary transfer function of the region checks whether the region is bigger than a certain size, or the number of parts in a region are bigger than a certain size, in which case the transfer function uses the mean over parts solution to improve the precision of the analysis. This differential treatment of regions can also be done depending on the importance of optimizing a particular region of the code. For example, the innermost loop, you may want to use more precise transfer functions than the rest of the program. Here's another example of region-based region transfer functions, and this is procedure summaries for interprocedural analysis. One way to tackle interprocedural analysis is to pretend that there is a control flow graph. There's a control flow edge from the call site to the entry of the callee function, and there is a control flow edge from the return of the callee function back to the return site, or the instruction that is after the call site. And that basically, the problem with that is it creates spurious paths that were not actually present in the original program, that thus leading to imprecision in the analysis. The other way to deal with this is to basically summarize the transfer function of the entire callee. So then recall that we create a region for the entire procedure. So you summarize the transfer function of the entire callee, and then at every call site where callee is being called, I just use out equals fn. Assuming it's a forward data flow analysis, I just do out equals fn. And so if there are different call sites, there are different invocations of different copies of the same function, and they don't interfere with each other, thus improving the precision of the analysis. So that's another example of a summary transfer function. And these three examples, symbolic analysis of loops, mean over parts, and procedure summaries, are three very canonical examples of why region-based analysis is very helpful in typical compiler optimization tasks.